We're going to go down the list of intermolecular forces until we find one that applies to BeH2. If we start at the top of the list and go down, we're going to guarantee that the first one we get to is the dominant intermolecular force. Now, a lot of people get confused, and this is something that I struggled with a lot when I was in the class, because intermolecular forces are named based off of the two different molecules participating in the force. 5A only gives you one molecule. What does that mean? That means that BeH2 is being attracted to BeH2. It is both molecules. I shouldn't draw a line, I should have dotted a line. So we want to know what is the interaction between BeH2 and BeH2. This eliminates some of the options. Why? Because if my two things are the same, there are a few of these that it cannot be. It cannot be ion-dipole, because ion-dipole means thing 1's an ion and things 2 a dipole, and if they're the same, they wouldn't be. You can't have one ion and one polar. So, likewise, it can't be dipole-induced dipole. So that narrows down our search a little bit. Okay, so let's look at BeH2. The first question to ask myself is BeH2 an ionic compound or a covalent compound? Well, I believe BeH2 is a covalent compound, which means I know it is not ion-ion. We already established that it can't be ion-dipole. So the next question to ask is BeH2, does it have hydrogen bonding in it? I would look at this, does it have a OH, NH, or a FH bond? It doesn't, so it can't be hydrogen bonding. All right, so I'd go down to my next one, dipole-dipole. So the question is BeH2 polar? How do I figure that out? Well, hopefully either you knew this for test 2 or you figured it out as a result of test 2. But if I want to figure out if something is polar or nonpolar, I need to draw the Lewis structure. So if I'm going to draw the Lewis structure for BeH2, it looks like this, I believe. So then I look at this, I think about the shape. What is this shape? Well, it's linear. And if it's linear, that means that this molecule is nonpolar. If it's nonpolar, what can it not be? It cannot be dipole-dipole. We already established that it can't be dipole-induced dipole. Therefore, BeH2 must be London dispersion. Okay, makes sense. Let me do another one. Let's do pH3. pH3. I'm going to erase these so we can go back through them. What can we automatically rule out? Well, if I'm only given one molecule, it can't be ion-dipole and it can't be dipole-induced dipole. All right. So is pH3 ionic or covalent? It is covalent, so it cannot be ion-ion. Can't be ion-dipole. Are there any FH, OH, or NH bonds in it? No. Then it can't be hydrogen bonding. Now, is it polar or nonpolar? How do we figure this out? We need to draw the molecule. If I draw pH3, looks like that. Okay, polar or nonpolar? Well, what's the shape? It's trigonal pyramidal, which means that is not a balanced molecule. So I would call that polar, and because it's polar, the dominant intermolecular force is going to be dipole. Okay, let's do one more 5E on there. CrCl3. Let's go through. Is it ionic or covalent? It is ionic, which means I'm done. All right, one thing to note just for smart work purposes, everything has London dispersion going on, okay? Whether it's ionic or polar or hydrogen bonding or nonpolar, it's got London dispersion going on. So when you're doing smart work and it asks you to choose all that apply, London dispersion should always be an answer. It's just in nonpolar molecules where it is the most dominant intermolecular force, if that makes sense. But everything's got it. Additionally to that, another thing for smart work is if something is hydrogen bonding, you should also check dipole-dipole, because like I said, hydrogen bonding is just a really strong form of dipole-dipole. So if it's got hydrogen bonding, then it has dipole-dipole in it as well. Okay, let me take a look at this homework and see if there's other ones that I should help you understand.